Yep. Hello, everybody. Thank you for coming for my talk. And so thank you, Sergey, for the introduction. Yep, my name is Dmitry, and I'm working for a company called Galia. We are actually outsourced for open source. And today I'm going to give you a short but tech deep dive into the compiler stuff, JIT stuff, and running JIT where Wasm faster, running JavaScript. So JavaScript is getting popular, yeah, you all know, especially in a WebAssembly community. So if you see the state of WebAssembly from 2021 to 2023, so you will see that JavaScript is getting more and more adoption, even for compiling to WebAssembly. And how to run JavaScript inside of WebAssembly? Because you can't run it directly, so you need some kind of runtime. So one option is to use Mozilla SpiderMonkey. It's a good choice. Or you can use QuickJS. There are, of course, other options like Dike tape, AUT compilation, but they are too experimental or too small. So SpiderMonkey is like a new, good Ferrari. So it has a comparable big size, around 5 megabytes. It supports only interpreter mode, compiled it to WebAssembly, because there's no any code generation. And it actually provides perfect support of all JavaScript features and the standards, because it's actively developed and under Mozilla company. From other side, you can have a QuickJS. It's very small. It supports to only interpreter mode, compile it to WebAssembly. It has less support of JavaScript standards, because there are no any big company under QuickJS yet. And it has a very fast interpreter. It's very fascinating stuff, and it provides a support for preprocessing your JavaScript into bytecode. And there are several issues with only JavaScript interpreters. So they provide slow math. It has an overhead on a dispatch, so all these interpreters are just switches in C++, so you need to dispatch on a dispatch block for every bytecode. It has no any specialization, and so no any optimizations. And what we want actually is to have a better than interpreter throughput. We want industrial support of new features of JavaScript standards, and we want it for free, of course. And we want a reasonable size and preprocessing or even AUT support. So I'm introducing you the JIT support for JavaScript with WebAssembly. So what we are going to do, we will take a SpiderMonkey, compile it into WebAssembly with WASI target, and it supports a lot of architectures for a JIT code generation, like x64, ARM64, RISC, etc. And we are going to add another target for SpiderMonkey, like Wasm, so that it can produce Wasm bytes for your JavaScript code. And at that point, you can say why, or what is going on, because SpiderMonkey is also a Wasm engine that can produce as a codegen your Wasm bytes, and it's a bit tricky. But if you see at the solution, you will see that it provides industrial support of JavaScript. And if you implement a Wasm backend, we will have interpreter for a cold code and a JIT for a cold code. And we will still have a big size, but we will talk about that in the last section. So how can we add a Wasm backend to the SpiderMonkey? So let's see to the internal picture of SpiderMonkey. So when you compile your source JavaScript into, not compile, you run with the SpiderMonkey, first of all, it compiles it to bytecode. Then it goes to C++ interpreter, and then you have 4 JIT tiers for execution. And all these tiers are using the one abstraction that's called macroassembler. And from this macroassembler, it generates bytes or assembly for execution. So what we need to somehow translate macroassembler into WebAssembly. And it's not easy to do because it's a very different architectures. So let's compare them. So the macroassembler have conception of registers of a hardware machine, and in Wasm we have only locals and globals. We don't have any control of hardware registers. And in Wasm we have a direct stack access. For example, we can unwind a few frames, and it's easy to done. It's easy to do, but in WebAssembly we have own restricted stack that can be manipulated only with WebAssembly instructions. But hopefully we have almost a similar set of instructions on both sides. And in macroassembler we have like assembly-like language. So it's labels, jumps, jump by addresses, and in WebAssembly we only have structured control flow. So how could we translate one to another? Let's start with the control flow. So this is a piece of macroassembler code, and if you see it, you can actually, if you are familiar with assembler, you can see that it's possible to use labels, information, and reconstruct the control flow graph from it. So each time you jump to a new instruction, to a label, you create a basic block. And each time you bind this label, you also create a new basic block with another set of instruction. And so you can reconstruct control flow graph from a macroassembler. And then if you sort this simple graph topologically, you can actually emit directly a block structure in WebAssembly. And so, yeah, it's how it's doing. And also want to note that since JavaScript is a JavaScript in SpiderMonkey produces only structured control flow graph, and our control flow graph obtained from a macroassembler, it's also structured. So we don't need to apply some fancy stuff like relooper algorithms and etc. And if we use some compiler, classic compiler algorithms to lay out this graph with loops, it's a bit tricky, but doable. We can have actually a direct mapping from macroassembler to WebAssembly. Registers. So when we compile JavaScript into macroassembler, macroassembler uses registers. And we experimented a lot with how to represent them inside of WebAssembly and came up with an idea of representing registers as a parameters of function. So each time when we call a function inside of WebAssembly, we pass this set of fixed parameters that represent registers. And why it's that? Because of the performance. Because when we compile this WebAssembly code to actual bytes, we can, for example, Wasm time can allocate real registers for these parameters because it's a parameters of function. And stack. So SpiderMonkey maintains the native stack. Its stack supports of like saved frame pointers, return addresses, locals, arguments, and etc. But in Wasm we have only like restricted stack with locals, intermediate values, and etc. And what we are going to do, we are going to maintain the same stack structure in a linear memory, as it is done in SpiderMonkey compiled to WASI with interpreter. And by importing the stack pointer value from a SpiderMonkey from a C++ version of SpiderMonkey. And so we will have two equal stacks, bytes by bytes, and so it will help us in the future to provide a better support for garbage collection, for unwinding, for exceptions, and etc. And so there is shortism of a compilation. So we recreate control flow graph from macroassembler. We used structured property of SpiderMonkey to lay out all blocks without any virtualizing program counter. And we represent registers as a parameters and maintain almost the same structure as SpiderMonkey natively would do. And so how can we then install this code? Because WebAssembly can't instantiate new bytes inside of WebAssembly. You have to run the host code. Luckily, Wasm time is able to compile and instantiate new Wasm modules at runtime. So we will see how to patch SpiderMonkey a bit to install new code. So let's see how SpiderMonkey internally call code when it compiles it to WebAssembly. So when we execute a source.js, it's going to spidermonkey.wasm, and this spidermonkey.wasm has its own WebAssembly memory and its own WebAssembly table. And then, if we have a compiled code for source, we will go to JIT. If we don't have a compiled version for this code, we will go to interpreter. And so, if we have a compiled code, we have to emit a colon direct and load from memory. Why is that? Because in Wasm MVP, it's only way to indirectly call a code, and this code can be changed at runtime, and it's why it's called indirect with load. So if we have a freshly instantiated Wasm modules for our compiled code, we can export this Wasm memory and Wasm table, extend the table, actually calling table grow, with a new function, and then patch a memory of original SpiderMonkey with setting some Boolean flags that we have a compiled code for this source.js. So the next time we will execute with SpiderMonkey this source.js, we will go to the compiled code that we provided from our Wasm module. And the next question is to when to call the compilation, because if we call it each time on each request, it will be a lot of Wasm modules, and it will be very slow. So we come up with an idea of a so-called asynchronous compilation model. So we have a Wasm time driver that instantiates the SpiderMonkey Wasm module. So then you execute your source.js, it returns a result. You do it many times, and at some point of time, SpiderMonkey decides to compile this source.js, and we postpone this compilation for some time in future. And when we are going to, in some next future, we can, from our Wasm time driver, run all pending compilation from SpiderMonkey, and then instantiate all these bytes and execute source.js with a JIT this time. So we are batching all compilation together. And what about results? I know that benchmarking is some kind of piece of art. It's not like a science. And so be prepared. And we are measuring throughput. So we warm up our code a little bit, so we can compile it version of all operations. And so you can see the difference between C++ interpreter in SpiderMonkey compiled to WebAssembly and our JIT version. Our JIT version significantly faster. You can see a few actually benchmarks from Octane, especially prepared for this talk because it's benchmarking with a lot of heavy calculations. And in general, a lot of faster, like 5 times or sometimes even 11 times, sometimes even faster. And why is that? Why we are providing so fast throughput? Well, because JavaScript is a very dynamic language, and SpiderMonkey supports a lot of optimization and specialization for known types. So it provides cache-IR support. So it's a way to implement specialization in SpiderMonkey. So we get it for free because we implement the macro assembler that is used by cache-IR. And we apply some tuning optimization. For example, between our compilation calls, we know that no any new code will be generated. And so we can apply, for example, inlining for known targets. For example, we always can inline the first call to the first IC operation in the IC chain. from SpiderMonkey. What about readiness of all this solution? We don't support the whole JS yet, but we pass 83% of internal JIT tests from SpiderMonkey. We are actively working on upstreaming all this stuff, so see this bug for any news. And how to use all of this? Yep. We have 3 interesting modes of execution. The first mode is called full specialization, the second one called the sharing scheme, and the third one call compilation each time. So in a full specialization mode, we will provide you a SpiderMonkey, compile it to Wasm, and you provide your source.js. And you can, or actually it will be better if you provide some test data for your source.javascript. In some cases, and it's easy to provide some test data. For example, if you are compiling your TypeScript into the source JavaScript, you know all the types. Or, for example, you're using component model and you know the real type that is going to your function in JavaScript. And we will provide you a fully specialized, only one WebAssembly module that is the compilation of SpiderMonkey with all of JIT, JIT modules together. It's good because you can then disable any runtime code generation if needed. You have a full support, full power of JIT with baseline and all kind of ICs. And you will have a full isolation because it's a one module per your source.js. But it still has big size, around 5 megabytes. Yep. Okay. The sharing scheme. The workload is similar, so you provide SpiderMonkey, source.js, and test data, and then we can generate you a very small JIT module. So then, for example, in a cloud environment, you want to execute your source JavaScript, for example, for a client, and you already AUT compiled this JIT module for this particular client with source.js, and then you can instantiate a shared version of SpiderMonkey, install this very small module, and it's a phase called setup phase, and then you can execute source.js with JIT. And this setup phase is very fast because we are using Visor and incorporate all of the JIT runtime into SpiderMonkey already ahead of time. The sharing scheme is it's what it's called. It allows you to share the all runtime code of SpiderMonkey between all clients. And you still need one instance per client for isolation and security reason. And this JIT module you need to use to provide JIT code to your SpiderMonkey. OK. Yeah, and the third mode of execution called call compilation each time. It's actually an emulation of how native SpiderMonkey works for tests. It's very slow, but we can use it for tests to replace the shell inside of SpiderMonkey with our custom shell, and we can run all kinds of tests inside the SpiderMonkey. Okay, and that's a short resume of what we've done. So we implemented a new Wasm backend for SpiderMonkey. We supported ICs and provided promising perf results from 2x to 11x. So why from 2x, not from like 1x? Even for a simple console.log hello world applications, you are still doing lookup, like console.log. You are finding log object, and this is done through the cache IR, and so we are fast at it. And we are passing most of the JIT tests and continue our development and provide interesting modes of execution or for cloud, or for embedding. And right now, we support only the first JIT tier, but theoretically, we unblocking the higher JIT tiers, like Warp or Ion. And I want to say thanks for all people from Shopify who sponsored this work, especially to Mike Xavier and Saul Cabrera, who patiently provide us feedback for our work. And I want to say thanks to SpiderMonkey team who reviewing and providing feedback for our design documents and our patches. And yep, I'm happy to hear your opinion about all of this.
Hello, awesome presentation. I'm super excited about your work. I wonder if you have thought of inlining the WebAssembly itself into the previous WebAssembly, so there are no further calls needed.
Could you repeat? Sorry.
Have you thought about the inlining the generated JIT WebAssembly inside of the runtime one, instead of the component one, if that makes sense?
Don't know. Actually, do you mean inlining inside of our generated code or inlining into the runtime?
Yeah, inlining the generated JIT code inside of the base one, inside of the SpiderMonkey JS plus, I don't know, whatever.
Yeah, we already doing that.
Okay.
So when we provide the SpiderMonkey for shared scheme, we pre-generate all JIT runtime as a JIT module. Then we merge these two modules together, so we don't do table grow and etc. We just incorporate all this into one module, so then it can be done, could be instantiated faster. Yeah.
Awesome, thank you.
Do you have to add more APIs on the host side to support compilation?
Yes.
Okay, so it's WASI plus some extensions that enable this.
It's just WASI plus some exported function added to SpiderMonkey C++. It's
Actually, following that question, do you see an option, a sensible API that would be cross-language that could enable JIT compilation?
I don't know. I don't think it's possible for any language here. It's only applied for SpiderMonkey, and it needs to be done inside of one engine. Yeah.
Yeah, no, but conceptually, do you see the possibility of having a generic API that could be used by different JITs?
Yeah, why not? Yeah. Yep, so thank you.